It's time for Dr. White's Fun with Graphs. This time we are going to talk about planarity, which is trying to draw graphs in the plane. And this is mostly going to be a review lecture, but the goal is to see how to tell whether or not a graph is planar. So recall that a planar drawing of a graph is something like these two. You have drawn all the vertices and all the edges such that no two edges are intersecting. So a graph is planar if it can be drawn with a plane drawing like this. So this is the graph K4. The standard drawing that one uses initially is not planar because we see these two edges cross. But here are two different plane drawings of it. And one, we just took one of the vertices and moved it a little bit to the middle of a triangle. In the other drawing, we just took one of the edges and bent it to go around the outside. And both these are valid plane drawings. And so it's important to note that a graph is planar if it has at least one plane drawing. And so to show a graph is planar, you have to mess around with the picture until you get it to look planar. As another example, here's K23. We see it's also planar. If we take one of these vertices and move it down, you end up getting this picture. And so it is a planar graph, even though this standard picture is not a plane drawing. So in general, you could ask yourself, given a graph, how do you determine if it's planar? Well, it turns out, at least for the purposes of this course, what you do is you just try to move the vertices around. I see that there's a crossing in this case, but the crossing could be removed if I just move this vertex inside the square, which is what I'm going to do. This is the same graph, but now it's planar. And one thing we had discussed in class was Euler's formula. So if G is connected and it's planar, so you have a plane drawing of it, then in that plane drawing, if you take the number of vertices, subtract the number of edges, and add the number of faces, you always get 2. So in this case, we had 5 vertices. We've got 1, 2, 3, 4, 5, 6 edges. And we've got 1, 2, 3 faces. The 4 cycles, and then the outer face. And so F is 3. And so if you do this subtraction and addition, you see you do in fact get 2. As we discussed in class before, and you can find the proof on Wikipedia, this actually tells you some information about a planar graph. If a graph has a plane drawing, then the number of edges is bounded above by 3 times the number of vertices minus 6. Or as an extra credit homework problem, if G is bipartite, you can get the bound to be at most twice the number of vertices minus 4. And the idea behind that proof was to triangulate the graph. So whenever there were cycles that bound a face that aren't triangles, keep adding in diagonal edges until you get nothing but triangles. So now we have almost nothing but triangles, but the boundary of the outer face is the square. So we need to add in one more edge. And now we see nothing but triangles. And then if you count the number of edges in this resulting graph, you will see that this bound actually happens. That we added 3 more edges, so we have 9 edges, and we had 5 vertices, and 3 times 5 minus 6 is 9. And so, in general, that's how the proof goes. You triangulate the graph, and then you actually get equality, and the equality comes from double counting and using this formula, and the fact that each face has 3 edges on it. And the upshot of this formula is that it can give you a way to show something is not planar. For instance, take the complete graph on 5 vertices. It has 5 vertices and 10 edges because it's a binomial coefficient. And 3 times 5 is 15. And when you subtract 6 from that, you get 9. And 9 is less than 10. And so these two numbers don't match up the way they're supposed to. And so that tells you that K5 is not planar. There's no way to draw it in the plane. Likewise, this bound on the edges tells you that K33, the complete bipartite graph with 3 vertices in each partition, also can't be drawn in the plane. because the number of edges is 9, and this bound gives you 8 because the number of vertices is 6, and 8 is not bigger than 9, and so you can't draw that graph either. And while we won't cover it, there actually is a polynomial time algorithm that, given a graph, determines whether or not it is planar. And actually there's polynomial time algorithms to draw a plane drawing of a plane graph, but we won't cover them because they're actually slightly complicated. And usually the idea, if I remember correctly, is that you try drawing one of the cycles and then you cleverly draw inside and outside, but usually it's a little hard to do it. So as I already noted, K33 is not planar because it's bipartite, and so our bound doesn't work. But what about these other three graphs? Are these planar graphs? Yes or no? If you think it's planar, you just have to move the vertices around and the edges around. And so this graph, this isn't a plane drawing because of this intersection. And so there's two possible ways to fix it. One way is to take one of these diagonals and remove it. I'll indicate that by marking it out and then adding the edge to the outside. That would give you one plane drawing. Another approach, switching back to the pencil, is to move this outside vertex inside. And that will also give you a plane drawing. Thus we see that graph actually is planar. What about the next graph over? Well, if we count the number of vertices, the number of vertices is 6. The number of edges is 10. So it doesn't violate our bound. And so we can't conclude that it's not planar. We see that the, let's see here, that twice the number of vertices minus 6, 3 times the number of vertices minus 6 is 12, and so we don't get a problem here. But notice what happens if I were to erase this edge. I now have K33. And so one thing you are allowed to use is that if you found a subgraph that's not planar, then the bigger graph is not planar, right? Because if you found a plane drawing of the bigger graph, you found a plane drawing of the smaller graph, and you already know you can't do that. And so there is an if and only if theorem called Kuratowski's theorem, which we don't cover in this course because it's actually in depth, but it basically goes along this line of saying that a graph is planar if and only if you can't find a graph that looks like K33 or K5, but the definition of looks like is actually quite technical. But if you manage to find K33 or K5 as a subgraph, then you know you're not planar. The other way you know you're not planar is if you have too many edges. So in this third graph, if you count it, we have 6 vertices again. And if you count it, there's 6 edges on the outside cycle and 2 triangles. Each of the triangles has 6 edges. And then there's 1 edge going across. And so that is 13. But we already did the calculation that 3 times 6 minus 6 is 12. So we have too many edges. And so that tells us that this graph is not planar either. And so our answer should be yes, no, and no. And those are our explanations. In one case it's because we found a subgraph that's not planar. In the other case it's because we had too many edges. And in the other case, we actually found a plane drawing. And so that's how you show if a graph is planar or not without using Kuratowski's theorem. And as we can tell, one nice fact about planar graphs is that there's no crossings. And so you can tell where the vertices are whenever 2 edges meet. There's a vertex there. Whereas when it's not planar, it's a lot harder to tell. You really have to make the vertices distinct and clear. And so having planar graphs is nice, but they don't always exist.